Hello VMSG and Happy New Year. My name is Gerallt Hughes and today I'll be discussing some of the results from my PhD project, which I recently finished, on the timescales of magmatic processes at Volcán de Colima in Mexico. Thank you all very much for being here today to listen to my talk. As you may be familiar, Volcán de Colima is an active stratovolcano in western Mexico, and its recent 2013 to 17 eruptive phase was characterized by dome growth and destruction cycles, lava flows, pyroclastic flows, volcanic explosions, and ashfall. These present significant hazards to the nearly 500,000 people who live near the volcano, and despite being a well-monitored and relatively well-researched volcano, fundamental aspects of the plumbing system are still poorly understood, such as the magma recharge and mixing processes, and these are key to accurately interpreting the monitoring data and understanding the future hazards. Therefore, in this talk, I'll be discussing some of the results of our diffusion modelling to understand these magmatic recharge events in the plumbing system and how we can correlate this with monitoring data to gain further insights into the dynamics of the plumbing system. The rocks erupted during the eruption are relatively homogeneous andesites containing plagioclase, orthopyroxene, clinopyroxene, iron titanium oxides, and rare resorbed olivine and amphibole, with a consistent mineral assemblage throughout the eruption and no major changes in bulk composition from 2013 to 17. However, when we look in more detail at the crystal cargo, in particular at the pyroxenes, we can see a much more complex picture, with 7 main pyroxene phenocryst populations, 6 zoned types plus a homogeneous type, and zoning is associated with an increase in magnesium number and chromium content suggestive of mafic recharge events, mixing, storage and remobilization processes in the plumbing system. Combining these observations with constraints on the pre-eruptive storage conditions using thermobarometry and integrating pre-existing models, our paper from 2021 proposes that mafic magmas and melts are periodically injected into a dominantly evolved magmatic environment, with most of the mixing to form the complexly zoned crystals occurring in the mid-crust. This is coincident with a large low-velocity body at this depth in the crust, as identified by geophysical studies, where ascending magmas are thought to stall before ascending again to shallower storage regions at approximately 6 kilometers below the volcano. But what we really want to know, in this study at least, is whether these mixing events have any influence on the eruptive activity and whether we can see this in the monitoring record. For this purpose, we use diffusion chronometry to constrain the timescales of storage and identify periods of recharge. As shown in the left-hand figure, the data indicate that there is a clear difference between the timescales of storage in the evolved and the mafic magmas, with storage in the mafic magma on the order of 1 month to 1 year, versus storage timescales of decades to centuries in the evolved magmas. The first-order interpretation of these data indicate that the long-term storage of crystals occurs within the evolved end member, and agrees with the interpretation that this evolved magmatic environment comprises the bulk of the system. The shorter timescales for reverse-zoned crystals also suggest that the mafic injections are transient events, and that after crystallizing the mafic rims, they are typically erupted shortly afterwards. We can see that the vast majority of the reverse-zoned crystals have timescales of less than 1 year, as shown on the right. But when we look at these timescales in detail, we can see that there's not one peak in these timescales, and we interpret this distribution as potentially being the result of multiple injections into the subvolcanic plumbing system prior to eruption. If we now focus on the reverse-zoned crystals, we can use the residence times to calculate approximately when the injection events occurred. As we know the eruption dates, and we know how long these crystals have resided in the mafic magma, we can therefore use this data to calculate the approximate date of when the mafic recharge events occurred in time. The clustering of the data suggests that there have been 3 broad periods of mafic recharge between 2013 and 17. Period 1 at the end of 2013 to early 2014, period 2 in late 2014 to mid 2015, and period 3 in late 2015 to early 2016. If we focus in detail at the different recharge periods, we can also see clusters of data, perhaps suggesting discrete recharge and mixing events within each period. For example, for period 1, marked out in the red box in the top left-hand corner, we can see only a relatively small number of timescales suggesting mafic recharge, and only one cluster prior to the eruption of several concurrent lava flows in the summer of 2014. This suggests that in the months leading up to the eruption, a small recharge event is indicated to have occurred. However, this does not appear to have been a major recharge event, as indicated by the low abundance of reverse-zoned crystals and hence the low number of timescale estimates for this eruptive period. For period 2, Reverse-zoned crystals were far more abundant, and hence we have a much larger and more robust data set of timescale estimates from different units. What we can see is that during this recharge period, there appears to be 3 clusters in the data, indicating the presence of 3 individual recharge and mixing events, which could potentially be interpreted as priming events in late 2014 and spring 2015, and a cluster of data of short timescales of approximately 2 weeks to 1 month, which may have provided the trigger for the eruptions in the summer of 2015. The events which effectively end this recharge period include the very intense and energetic July 2015 event, which comprised explosive eruptions, the collapse of the lava dome, and the emplacement of a 10-kilometre long pyroclastic flow deposit, immediately followed by a lava flow on the southern flank. The higher abundance of reverse-zone crystals, combined with a timescale suggesting recharge and mixing in the months prior to the eruptions, could suggest that the pyroxene phenocrysts are recording the ascent and mixing of hot, volatile-rich magma, which then ascended into the crater and into the conduit, which drove the more powerful eruptions. And for period 3, we can see a similar pattern of timescale clusters indicating 3 recharge and mixing events in the months prior to the lava flow in 2016. Similarly, these clusters of timescales may represent 2 priming events in late 2015, early 2016, and in March to June 2016, followed by a cluster of short timescales which may represent the trigger in August of that year. Whilst the patterns of the data appear similar to period 2, the eruptive behaviour is very clearly different. The 2016 lava flow was a mostly effusive event, although one with much more frequent explosions than the 2014 lava flows. But why is there a difference between the 2015 event and the 2016 lava flows, but with a similar recharge pattern? To help us answer this question, we have combined the timescale data for the mixing periods with the volcano monitoring record. We can see very little change in the monitoring record during period 1, with no apparent association with the different mixing events, suggesting that this recharge event may not have had much of an impact on the magmatic system. This contrasts with period 2, where shortly after the start of the recharge there appears to be a sudden increase in gas emissions, tremor, and other seismic events. This pattern suggests that the start of the mixing period was associated with volatile separation, increased degassing, movement of volatiles, fluids or magma through the magmatic system, and later on to eruption. Period 3, on the other hand, appears to have less well-defined patterns, but certain mixing events can be correlated with small increases in gas flux and seismic events. Tentatively, we propose that the different mixing events may have heated the reservoir sufficiently to allow more efficient volatile separation, resulting in more degassed magma ascending through the plumbing system to erupt more effusively. Curiously, during the entire eruptive period, there appears to be an absence of deep seismicity below the first few kilometres of the crust. This may reflect an absence of intrusion, however, this is not supported by the petrology, and we instead suggest that the high temperatures and a mechanically weak crystal mush may result in plastic behaviour at depth. Interestingly, despite an increased gas flux and magma injection, there appears to be almost no surface deformation during this period, which may possibly indicate the presence of an exalted volatile phase. However, much more work is needed to test these ideas. And I'd love to discuss with you in more detail, and further work should include investigating the volatile behaviour at Colima, constraining the ascent rate of the magmas, and comparing this phase to the Plinian and other interplinian phases, which will be very important for volcano monitoring at Colima. And if anybody has any questions or ideas, please feel free to contact me. I'd love to hear your thoughts. Thank you very much. Thank you.